Thank you for watching our video that is part of the WEC-Sim technical training course. In this video, we will be discussing the theory and workflow of WEC-Sim. To start, we want to make sure that viewers are familiar with WEC-Sim, or the Wave Energy Converter Simulator. WEC-Sim simulates wave energy converter dynamics in operational waves. It is a time-domain, rigid body equation of motion solver following the Cummins formulation for implementing the hydrodynamics. The software is built in the MATLAB Simulink environment and is hosted on GitHub and can be found at the following link on this slide. This project, or WEC-Sim, is a joint NREL-Sandia project funded by the U.S. Department of Energy Water Power Technologies Office. The first release of WEC-Sim came out in June 2014, with our latest release happening in this past September 2022. To start, we want to ensure that users know the coordinate system that WEC-Sim uses. On the right, we have three images of an isometric side and top view of a sample wave energy converter that consists of a floating body that is attached to the seabed. Now, the positive x-axis follows the direction of wave propagation. So that means that waves will be coming from the negative x, passing through or hitting the body, and exiting in the positive x-axis. WEC-Sim follows with the z-axis as positive in the vertical direction, with 0 at the still water line. And with the definition of the x-axis and z-axis, the corresponding y-axis follows the right-hand rule. For any of the position, velocity, or acceleration vectors, the outputs from WEC-Sim will be a 1/6 vector, and the first index of that vector will always correspond to surge, or forces or motion in the x direction. The second element in the sway, or y direction. Third element, heave, or the z direction. The fourth element, roll, or rotation about the x-axis. Index 5 is pitch, or rotation about the y-axis. And index 6 is yaw, or rotation about the z-axis. The image here shows the WEC-Sim workflow, which we'll go over in more detail. The first step in building a WEC-Sim model is to start with generating a 3D mesh of any hydrodynamically active body. We then calculate the hydrodynamic coefficients using that 3D mesh using a BEM solver such as WAMET, Aqua, or NEMO. After we have run the BEM solver, we are going to create an HDF5 file using our Beamio script. If you want to visualize the animation in WEC-Sim or use our nonlinear hydrodynamics option, you will also need to create a .stl file. The next step in the workflow is to build a WEC-Sim model in Simulink. The Simulink model will consist of the various blocks that are described and highlighted in the image here. Next, the user must write and fill out a WEC-Sim input file and potentially a PTO sim input file, where you are defining the various classes that are highlighted here in the image. Once the Simulink model and the WEC-Sim input files have been written, the user can now execute WEC-Sim by typing WEC-Sim in the MATLAB command line. Once WEC-Sim has been executed, the first step is for WEC-Sim to read your WEC-Sim input file, which reads your inputs and then activates the specified variant subsystems within the Simulink model. With all of the variant subsystems triggered and active in the Simulink model, MATLAB can then run the WEC-Sim simulating model to run the time domain simulation. After the WEC-Sim run is completed, WEC-Sim will output the output data structure that includes the time histories of the various blocks that are in your Simulink model. There is also the opportunity to generate a user-defined function where it will automatically calculate statistics, plot certain variables as defined by the user. Now that the WEC-Sim code workflow has been defined, we want to make sure that users understand the theory behind WEC-Sim. WEC-Sim uses the time domain equation of motion following the Cummins formulation to solve the dynamics. In the equation shown here is the general equation of motion, where mass times acceleration is equal to various external forces. These include the hydrostatic restoring forces, wave excitation forces, which is obtained from boundary element method solvers, radiation forces, which include added mass and wave damping, also obtained from BEM simulations, viscous forces, power takeoff forces, mooring forces, and nonlinear hydrodynamic forces. These highlight the various standard forces within WEC-Sim. However, because of the open source nature, it is fairly easy to add any other external forces that your system may require. The static or dry mass is highlighted here on the left-hand side of the equation of motion. The translational mass is a one-element input. The moment of inertia is a 1/3 element input that defines the dry properties of the WEC body. In the latest version of WEC-Sim, we do have the opportunity to define the 1/3 element product of inertia. For each body in the WEC-Sim input file, you must define the mass and moment of inertia. If you would like more information, please look at our training materials and look under body implementation. We also encourage you to look at the advanced features, body features, to see how we handle special cases. The hydrostatic restoring forces, highlighted here on the right-hand side of the equation motion, is calculated as the product of a hydrostatic stiffness matrix and a vector of displacements, as shown in the middle of this slide. The elements of the hydrostatic stiffness matrix, defined as K, HS, is defined for each body in the .h5 file, generally obtained from BEM outputs. Note that this is generally a linear implementation of the hydrostatic restoring forces, but you are encouraged to look at the advanced features, nonlinear hydrodynamics, for an alternative calculation method. The next external force is the wave excitation force, highlighted here on the right-hand side of the equation of motion. These are calculated from BEM results, which provide complex excitation force coefficients. For a single frequency regular wave that has a height h and a frequency omega, direction theta, and incorporating a ramp function r subscript f, and using the real component, the expression for the excitation force or moment, depending on the index of the motion, is defined by the expression shown in the middle of the slide. For an irregular wave or multiple regular wave scenario, using the spectral density S to define the wave spectrum and a random phase defined by phi, you can see in the lower equation how WEC-Sim calculates the forces in an irregular sea state. WEC-Sim does have the opportunity to import a wave defined by a time series. In this case, we use the convolution between the wave elevation and the excitation impulse response function to calculate the wave excitation force and moment time series, as shown by the expression in the middle of the slide. Again, we are taking the wave excitation coefficients from the .h5 files. WEC-Sim also provides the opportunity to implement a ramp function that allows the simulation to gradually increase the magnitude of the wave excitation forces to help with ramp up stability so that you do not see an impulsive force at time t=0. The next external force is the radiation forces, highlighted in yellow on the right-hand side of the equation of motion. The BEM results provides a complex frequency-dependent radiation coefficients for added mass defined by A and the wave damping divided by capital B. When oscillating under the excitation of a single frequency regular wave defined by a constant height h and frequency omega, the radiation forces can be simplified to the added mass coefficient at the oscillation frequency times acceleration, in addition to the wave damping at the oscillation frequency multiplied by the velocity of the body. If you do not have harmonic motion, and rather in irregular wave time history, we need to implement and follow the Cummins formulation, where we multiply the infinite frequency added mass, A infinity, by the body acceleration and calculate the time varying term with the radiation impulse response function, Kr, multiplied by the velocity of the body, where Kr is calculated from the wave damping values. WEC-Sim, by default, calculates these forces using the full convolution implementation, but WEC-Sim does also provide the opportunity for you to approximate the convolution term shown on the lower right equation via a state space approximation, which can improve the speed of a simulation and be used for control applications. If you'd like more information, we direct you to read Theory, Numerical Methods, State Space, which can be found on our documentations page. The next set of forces that WEC-Sim can model are viscous forces, again highlighted on the right-hand side of the equation of motion as an external force. WEC-Sim has the opportunity to model both linear and quadratic viscous forces based on coefficients and parameters defined in the WEC-Sim input file. The two forms, quadratic and linear, are shown in this equation. And the final equation shows that we are adding these two as independent forces and are non-interacting. These two forces are being calculated based on the body velocity itself. We do have the additional option of implementing Morrison elements, which also subtracts off the relative flow of the undisturbed wave velocity based on the linearized orbital motion. If you would like more information on this implementation, please look at our advanced features under Morrison elements. The next force included within WEC-Sim are the forces from a power takeoff system. This can also be considered the generator or motor that's providing the conversion from mechanical energy to normally electrical power or some other useful power. Now, the most simplest PTO model that WEC-Sim has is a spring damper system, where the PTO can apply a force on one or multiple bodies based on the displacement of the PTO, and a component related to damping, which is a coefficient multiplied by the relative velocity between one or more bodies. This relative velocity will be dependent on the type of wave energy converter system you have and how the PTO is coupled to the various degrees of freedom. We also can model a wider range of PTOs and can leverage the full suite of Simulink and Simscape components to have a higher fidelity model of various PTO designs. If you would like more information and would like to design a more complex PTO than the simple mass spring damper system highlighted in the equation above, we suggest that you please read our Advanced Features PTO Sim section. The next force included is forces from mooring or station keeping systems. WEC-Sim supports using a linear mooring matrix or moordyne, which is a lumped mass approach to model mooring lines. The linear mooring matrix forces are calculated following the equation below, where you have your mooring stiffness matrix, your mooring damping matrix, and a vector of pretensions in the 6 degrees of freedom for the moorings. And the forces will march through time as shown. Moordyne is more advanced, and we suggest that you look at the Advanced Features Moordyne description or visit the Moordyne page for greater insight into the calculation of the mooring forces. Another force that can be activated within WEC-Sim are the nonlinear hydrodynamic forces. These include the nonlinear Freed-Krylov and nonlinear buoyancy forces that are calculated based on integrating the instantaneous pressure over the body geometry. The body geometry is defined by a supplemental .stl file, and the pressures are calculated from the time-resolved undisturbed wave fields and instantaneous body displacement. For more information, please visit our Advanced Features Nonlinear Hydrodynamics description on our documentation webpage. This slide is a summary of all of the equations for the various forces and moments calculated within WEC-Sim. Please take a moment to pause the video if you'd like to look closer and re-examine many of these equations. We also direct you to our documentation page, where these are also listed with further description. Now that the various forces describing the theory behind the implementation of WEC-Sim, we want to quickly summarize how you would run a WEC-Sim simulation. Before running any WEC-Sim simulation, and these steps can be done in any order, you need to first generate a .h5 file which defines the hydrodynamic coefficients that provide the hydrodynamic forces to run the time domain simulation. You then need to build a Simulink or a .slx model that describes your device layout, such as number of bodies, number of PTOs, number of constraints, etc. Then you must write a WEC-Sim input file that defines the various dynamic parameters for each of the bodies that are included in the Simulink.slx file. We want to highlight on this screen that it is very important that the .h5 file be generated before running WEC-Sim and is a very important pre-processing tool, as the simulation is generally only as good as the quality of your hydrodynamic coefficients. Currently, WEC-Sim can support the following BEM codes, or essentially if you have the output structure from WAMIT, NEMO, Capitaine, or Aqua, our BMEO script will properly convert that format to a common .h5 file format that can be read by WEC-Sim. We want to highlight that BEM codes do generally require mesh or several meshes to run the BEM solution. A couple examples of codes that you can use are highlighted on the right. We also encourage you to read more about in the user manual, workflow, step 2. After you have completed the pre-processing steps and built your Simulink model and written the WEC-Sim input file, you can now run WEC-Sim. There are two ways you can run WEC-Sim. The first is by typing WEC-Sim in the MATLAB command line, or there is the option of running using our Simulink GUI. For more information, please see the advanced features running from Simulink section in our documentation webpage. Upon executing WEC-Sim, WEC-Sim will then clear any variables that might conflict with those that are about to be loaded, and then it will run initializeWecSim. Running the initializeWecSim script results in the following steps. The first is reading the WEC-Sim input file. Next is based on the parameters read from the WEC-Sim input file, set up all of the objects and body blocks defined in the Simulink.slx file, which includes bodies, constraints, PTOs, moorings, etc. For each hydrodynamic body, it will then load the non-dimensional hydrodynamic coefficients. It will then set up the simulation and waves class to calculate the corresponding wave time series. For each of the hydrodynamic bodies, it will then convert the non-dimensional hydrodynamic coefficients to dimensional forces. Next, initializeWecSim will complete a series of diagnostic checks to make sure that the inputs the user has defined are appropriate and will not result in the simulation crashing. Next, the initializeWecSim script will help define the variant subsystems. What that means is that we have, under various blocks that are found in the Simulink browser, several items shown on the right where you have a subsystem that has an output, but there's no connection to the rest of the Simulink model. The variant subsystems will, based on the inputs from the WEC-Sim input file, automatically be updated to create the right connections to make sure the correct forces based on the wave climate are being calculated. After the initializeWecSim is completed, WEC-Sim will then run the Simulink simulation to step through the time domain dynamics. You can observe the dynamics from the Simscape visualizer, or you can turn off the visualizer and wait for the post-process notification to be made. During the post-processing step, WEC-Sim takes all of the outputs that are in the Simulink model and outputs them in the response class. It will then save the results, and after that, it will run any user-defined functions written by the user to either calculate certain statistics automatically, plot certain time histories, or complete other custom features. Many new users will come across an error or warning message when running their first WEC-Sim model or potentially running a new model for the first time. Many of our common errors do have informative error messages that try to illustrate the mistake so the user can make the correction and try to rerun the simulation. Sometimes the error inputs or where they are found in the WEC-Sim file are not clear, and in this case, if you cannot discern that yourself, please visit our issues board and ask for clarification. As an example, the error shown in the above image is because the user was trying to define the quadratic drag vector, but it was the incorrect length. This video has tried to provide an overview on the theory and workflow of WEC-Sim, but understand that many viewers want more information on how WEC-Sim is used and the underlying theory. The various links shown on this slide will hopefully give you more information for you to solve any issues, build a new model, or answer any questions you have about the software. Thank you for your attention, and I hope you found this video helpful in learning how to use WEC-Sim. If you'd like more information or want access to any of our other webinar or training materials, please visit the following link here.